Good evening. We shall review for a bit. And for once, we have wonderful weather to go out and view the sky, and we're going to do that. So the test tomorrow will be over chapters 1 through 4. And so chapter 1 is about science and the universe. Saw the hand come up here, and I thought you were raising your hand for a question. So let's get into these things. How do scientists go about explaining things? Okay, we've already seen this slide, so let me go put all the pieces up here. So scientists start with pre-existing ideas. Remember, the scientific method has built on scientific ideas, not on just plain conjecture. And then when you come up with a hypothesis based on scientific ideas, you need to test it, so everything has to be able to stand up to tests. And tests go on forever. You're never done testing. You get more and more confidence if something continues to pass tests, but that doesn't mean it's right. It doesn't mean you've proven it, because you never do. Part of the scientific process is to report those results of experiments to scientists. There's the scientific literature. You report it there with detail so other people can try to reproduce it. Other people try to reproduce it. If they can, they start to believe that you're not lying. If they cannot, they don't believe you're lying generally. They believe that you were probably sloppy. You got something in there that you didn't know was there. So that's the basic scientific ideas. Scientific method, you know that you are going to have one question on the test that will be worth more than 10% of the score on the test. And that question has two parts. One is to list the 4 pieces of the scientific method as we've talked about them. So number 1 is observe something interesting. You're just going to have 1, 2, 3, 4, and you're going to write the things in. So observe something interesting. I put that in there. A lot of people wouldn't put that in. But I do, because that's an important thing. Scientists have to be curious. What's the next step after observing something interesting? Form a hypothesis that's based on scientific ideas that explains why the thing you observed occurred and makes testable predictions. I guess I should go ahead and go forward with each one of these things I've said now. All right. After that, devise an experiment that will test a prediction. You are not repeating the observation. You're devising a test of a prediction that you don't know necessarily what's going to happen. Question, Leslie?
What does falsified mean?
Falsified means that it's been proven incorrect.
Oh, so it can be tested and proven incorrect.
Yeah. You can never prove it correct, but you can prove it incorrect. So number 3 is to devise the test and run the test. And number 4 is determining if the hypothesis passed or not. If the hypothesis passed the test, you go back and you devise a new test of either testing the prediction a different way or testing a new prediction. If the hypothesis is proven wrong, if it's falsified, then you go back to step 2 and you develop a new hypothesis, because now you have more knowledge. Now you know, well, it wasn't that, so it must be this maybe. And so in this process, you are constantly developing better and better hypotheses as you prove pieces of it were wrong. So having an experiment disprove your hypothesis is not a major setback. It's a step forward in your understanding. Now, it still is very disconcerting when you're, let's say, doing your PhD research and you keep getting results that are contrary to what you expect. Look, nothing happened when my hypothesis predicted something would. Oh, great. But it's still, you're learning things with those results. Okay. We also had chapter 1, the terms models, theory, law. What is a model? Representative. Okay, I hate it when I do that. Yes, you can all read, but on the test you won't be able to. Where is the nearest model? Right there. Thank you. Yeah, if you're going to point to me, I'd say, oh, gosh. Yeah. Yes, that was a joke. Thank you. My wife was a model, just for the record, but not me.
Aw.
So a model is a representation of something. It's not the way it really works necessarily. The stars aren't really on a crystalline sphere that's rotating around the Earth. But we still talk about the celestial sphere model as a useful way to describe the positions of the stars. A theory, an explanation of how nature works. And theories tend to be, well, they're tested more and more, and we have pretty good confidence in most things we call a theory. You know, the theory of gravity. It's just a theory, which means that I am 100% believing in it. Now, do I believe in the theory of evolution? No, I don't. But I just want to point out that just a theory doesn't mean it's weak. A law is special in that you can make it in concise language, usually making it into an equation form like Newton's second law there. The sum of the forces, mass times acceleration. We'll talk about that a lot tomorrow, you three. And it needs to describe something that's very general to be a law. Last thing that I'm caring about for chapter 1 is just the size of things. You know, in our everyday lives, we live in this region of this graph. Now this graph, whatever you want to call it, this chart is in logarithmic scale. So the difference between this and this is very, very tiny. The difference between this and this is enormous. Yes, ma'am?
So you want us to know how to read those?
No. I just want you to understand the relative sizes of things.
Oh, okay.
The size of a proton is around 10 to the minus 18 meters. That's, 0.17 zeros and a 1 meters. Whereas, the size of a human, this is on the 1 meter line. Of course, most humans aren't 1 meters. We're closer to 2, right? 2 meters is about here. So, but on this scale, you wouldn't tell the difference. So that's the sizes we're used to. And then you get up there and you see it's not that far on this scale to get to the radius of the sun, the astronomical unit. What is an astronomical unit? Okay, the average distance from the sun to the earth. It is kind of important to say the average distance because the earth doesn't have a perfectly circular orbit.
Yeah.
It's maybe on the test 1/3 of the time, but it's one of my favorite questions nonetheless because it's so simple. If you know what it is, what's the different distance between the sun and the earth? What astronomical unit? Because that's the definition. In meters, an astronomical unit is 150 million kilometers. So going out there, we have the nearest star, other than the sun, is a little over 4 light years away. Now, a parsec's like 3.26, so it's a little more than 1 parsec away to the nearest star. Do you remember the name of the nearest star?
Wait for us?
The nearest star, not counting the sun. So the nearest star to the sun. This can be asked with tricky wording to get 2 different answers. The nearest is technically Proxima Centauri. Proxima, because proximal means close.
Do you want us to know that?
You should, yeah.
Proxima what?
Proxima Centauri. The nearest visible star is Alpha Centauri, which is close to Proxima Centauri.
So Proxima Centauri is the nearest star, but the most visible sun.
But the nearest visible one
star is the nearest visible one.
Is Alpha Centauri. So you'll see both things. And sometimes people say the nearest star, and they mean Alpha Centauri. Alpha, the Greek letter alpha.
Yeah.
Alpha Centauri. Remember we talked about star names. Well, I'm pretty sure we did. And with the Bayer naming method, Alpha Centauri means it's the alpha star in the constellation Centaurus. Centauri is just the possessive, so that means it belongs to Centaurus. And so it's the principal star, it's the brightest star in the constellation Centaurus. Yeah.
So technically, depending on the wording, if you said which one is the closest one and not which is the closest visible one, then you would be the...
I would be talking Proxima Centauri, yes. You say the closest visible star, then it's going to be Alpha. Okay. Going to bigger things, our solar system, you measure astronomical units, it's very convenient. Nearest stars, light years or parsecs. Talk about the size of the galaxy, we talk about thousands of parsecs. The nearest galaxy beyond ours, well, now we're getting into large numbers of light years. The farthest thing observed is in the billions of light years. So there's really big distances for comparison. And we have sizes of things. Remember, you had what's the biggest thing in the universe in one of the homework problems? I looked it up for your solutions. I hope you guys know that after the homework's turned in, if you go to the homework again, you'll see the solutions there. And the biggest thing is no longer the Sloan Great Wall. Since 2014, I don't remember what it is, but Sloan Great Wall is third or fourth on the list of biggest things now.
On the Earth?
But they're in the universe that are known. But they're collections of galaxies are the biggest things. Okay, chapter 2, the sky above us. We're going to go out tonight to learn more about the sky above us. Chapter 2, we learned about things like vocabulary words. So I'm going to have the next slide will be all those vocabulary words that I ran you through once before. You do need to know all of those. Those are easy questions to ask, easy questions to answer, as long as you learn the jargon of astronomy. Then we had ancient astronomy, the people involved. Astrology, why is astrology there? 2 reasons. Number one is because it's a pseudoscience. It's something that acts like a science but isn't really. They take scientific information, the position of the stars and the sun, and then they make predictions about people's lives, but there's no scientific connection between them. They don't have, this does that. It's simply, because the sun's there, this will happen. Also, the second reason is because the zodiac, what is the zodiac? You could say it in 3 letters. Starts with the same 2 as zodiac.
Zoo.
The zoo, yeah. The zodiac is the zoo. It's the collection of constellations that are on the path the sun takes as it goes around the earth. Of course, you realize the sun isn't going around the earth. But from our observation, it appears that way. And so that's, again, we're saying something imprecisely. Really, the earth is going around on that path.
Question.
Wait, so the zodiac is a zoo because it's a constellation? It's a collection of constellations?
It's the collection of constellations, the animals, that are on the path that we observe the sun passing through. And then we're going to talk about birth of modern astronomy. So here's a whole bunch of vocab words. So I'm just going to say the definitions for these. It'll take forever if I poke, each one. What's this mean? What does this mean? So an asterism is an informal star picture. There's no official catalog of asterisms. They're, Jim Bob said, "Oh, look, it's the," my mind goes completely blank. It's the Nissan Altima in the sky. It looks like an Altima to me. Or going to real things. It's the microscope in the sky. Microscopium. It's the triangle in the sky. Triangulum. Yeah. There's a constellation called, yes, those last 2 are actually constellations, not asterisms. They're really, really lame constellation names. Asterisms are star pictures. The picture that goes with a constellation like Orion, that picture is not considered an asterism because that's the picture associated with the constellation. But then you have Orion's belt. Yeah, that's an asterism. Okay, celestial equator. You just take the Earth's equator, pop it out onto the celestial sphere, and that's the celestial equator. So the celestial equator is the line on the celestial sphere that is directly above the equator on Earth. The celestial sphere, then, this model, the idea that we can treat observing the positions of the stars as if the stars are on this big sphere that is going around the Earth. Circumpolar constellations are constellations that are going around the pole, and never dip below the horizon. So the circumpolar constellations changes based on your latitude. If you are at the north pole of the Earth, then all constellations in the northern hemisphere are circumpolar because they're never going to set. Whereas if you are at the equator, no constellations are circumpolar because they're all going to set.
They go below the equator, you said?
They go below the horizon.
The horizon. Oh, they don't go below.
Okay, so a constellation is not a picture. It is an area in the sky. And every star belongs to one and only one constellation. And if you take all 88 constellations, you completely cover the area of the sky. So you have 4 pi-steradians, if you will. So you should know some constellations for lab. It's not going to be on the test. You're not going to have to name constellations. But you do need to know what a constellation is. And so like one of your homework questions, oh boy, it's graded, but I haven't got it returned yet, the homework 2. If they say an object was viewed in Orion last night, what does that mean?
Oh yeah, that was something that was in that constellation.
Yeah, it was seen in the area of the constellation. All right, declination. Declination is exactly equivalent to latitude, but for the celestial sphere. And so anything that's at your zenith, next to last word, zenith is the point directly over your head, is going to be at the same declination as your latitude. It's measured north from the equator or south from the equator, just like latitude is measured north from the equator, south from the equator. Diurnal motion means the daily motion. Because the Earth is rotating, it appears to us as if the stars are rising in the east and setting in the west. Oops. Rising in the east and setting in the west. Because the Earth is rotating toward the east. The ecliptic, I already talked about that path, that the sun appears to travel as we view it from Earth. Equinoctial couleur. One of the things that you have to point out in your lab final, that tonight I will point out carefully in lab. The equinoctial couleur is the line that is the equivalent to the prime meridian of the sky. That's where we measure east to west from, the reference point. It's the meridian that starts at the north celestial pole, goes through the vernal equinox, and goes to the south celestial pole. The horizon, well, everything is horizontal. Easy. Moving on. Meridian, line that goes from pole through your zenith to the other pole. Nadir, directly underfoot. The celestial poles, take the Earth's rotational poles, pop them out to the celestial sphere, and those are celestial poles. They're the points that appear to not move as the Earth goes through its diurnal motion. Right ascension, the equivalent to longitude, measured in units of hours, minutes, and seconds. That's hours of the day. You use a clock to measure it. The reason is because the Earth rotates, and you can use a clock. You measure what's at your zenith, an hour later, it's the right ascension that you had before, plus 1 hour. It's very simple in that regard. Vernal equinox, 2 definitions for the vernal equinox. One is the time when the sun crosses the equator, as viewed from us. The other one is the location on the celestial sphere where that occurs. So where the celestial equator and the ecliptic meet is the vernal equinox. Now there's 2 of them. There's the autumnal equinox. We're almost there. Autumnal equinox is, okay, I looked it up. Don't remember now if it was September 21 or 22 this year. I think it's September 22, my mom's birthday. So we're almost there. Summer is almost over. Because at the autumnal equinox, we change from summer to autumn. At the vernal equinox, we change from winter to spring. We name our seasons based on the equinoxes, probably a better plural for that, and the solstices. Solstice I don't have up here, so let's just make sure we got the solstice. Solstice is the extreme angle that the sun makes. So the sun varies between 23.5 degrees north and 23.5 degrees south of the equator. And so the solstices occur when the sun is at 23.5 degrees north. We would call that the summer solstice here in the northern hemisphere. And 23.5 degrees south, we call it the winter solstice here in the northern hemisphere. Okay, I talked about the other jokes. Moving on. Ancient astronomy. Ancient astronomers were not idiots. We tend to think, oh, they knew nothing. They didn't have all the sophisticated tools we have today. Remember, we talked about Tycho Brahe's state-of-the-art wondrous observatory, which was a building with a hole in the wall and a very carefully measured sighting instrument. It's nothing to what we have today. But just because they didn't have sweet instruments didn't mean they didn't have sweet minds. And so they observed things and they figured out, I say immediately, who knows? But they figured out long, long ago that there was a cycling to the seasons, that the seasons recurred with a definite period to it. And that period was roughly 365 days. And then from that 365 days, they get to 360 degrees in a circle because they thought 360 plus 365 is kind of magical. The seasons are marked by the solstices and the equinoxes. And if you look at ancient observatories or things that we think might have been observatories like Stonehenge, it is very clear that these were laid out with seasonal things like equinoxes and solstices built into how they oriented and made them. So those people knew a lot about the seasons and how the sky varied with the seasons. Just to make things clear, if you've watched National Treasure, people who make movies, once again, don't. They talk about the shadow where the sun is shining through this window when the hands of the clock are at this position. Well, it's going to vary every day. You better be there on the right day or it's going to be a different position. And of course, with the leap year system, it's a little more complicated stuff. Okay, so lunar cycles. Obviously, lunar cycles are they're obvious because obviously the obvious moon. I've tried to get obvious as many times as I can. The moon goes through cycles. If you're a flat earther, I believe that means that the light inside the moon gets brighter and dimmer, and somehow we only see parts because flat earthers believe that the moon is giving off its own light. Conventional science says the moon is reflecting sunlight, and we see the phases of the moon because of the geometry between the sun and the moon. What did ancient astronomers know? I'm not exactly sure. I don't know that anyone is. But we do know that people 300 years before the time of Christ had a very strong understanding of just these things I talked about. It's not some new modern wizardry to understand that the moon is reflecting sunlight. What's new in modern wizardry is the internet that allows people to propagate the crazy things about flat Earth. So lunar cycles, make sure that you understand the lunar cycles, what causes them, what they are, so you should be able to, like we have in the quiz, know that DOG acronym so you know by looking at the shape of the moon if it's a waxing moon or a waning moon. Make sure you know first quarter means a waxing half moon. Third quarter means a waning half moon. And the geometries of those. When they rise. I don't know if I talked about when they rise. The new moon, of course, occurs when the moon and the sun are lined up with each other. So the side of the moon we see is not lit up. As you go on through the cycle, at the beginning of the cycle when the moon is waxing, it's going to be in the sky a little bit before the sun sets, and it will be visible at sunset. And then when it's a full moon, of course, it rises with the sun and sets with the sun, and then it's going to be visible at sunrise after that. I sure hope I remembered that right. I know I told you. You should remember it. We haven't talked about this year, so I'm going back a year. But that's another thing you can determine the phase of the moon by when it rises and sets. Eclipses. What causes an eclipse? No flat Earth theories here. Okay, either the moon's shadow is cast on the Earth, in which case we call it a solar eclipse, or the Earth's shadow is cast on the moon, in which case we call it a lunar eclipse. And once again, these are based on geometry. The phases of the moon are based on geometry, so there's a timing. A new moon is always going to be the phase when you have a solar eclipse. A full moon is always going to be the phase when you have a lunar eclipse, which is kind of good because if it was a new moon and you had a lunar eclipse, it wouldn't be very exciting. I can't see the moon, but I'm pretty sure if I could, the Earth's shadow would be on it. Yay. Okay, some ancient astronomers. Aristotle. Aristotle, person who believed in this sphere, he thought that was the way it really was. He determined, some 300 or more years before the birth of Christ, that the Earth was spherical by looking at the shadow that the Earth casts on the moon during an eclipse. So it was no new thing back in 1492 to think that the Earth was a sphere. And then Aristarchus, a little bit later, by measuring things that he could, things like the time it takes for the moon to go through the Earth's shadow and eclipse, he was able to determine how big the moon was, how far away the moon was. He did those pretty accurately. Then he worked on how big and how far away the sun was. He was way off on those numbers. But still, that's pretty impressive, I think. Eratosthenes, we're talking more than 200 years before the time of Christ, Eratosthenes very accurately measured the radius of the Earth by using the shadows. Remember a shadow going down to the bottom of the well in Syene, meaning it's got to be directly at the zenith, measuring the angle for the shadow at the same time in Alexandria, comparing the angles with the distance between the two, and then just calculating, okay, it's that much of a circle then, what's the diameter of that circle? And then we have Ptolemy. Ptolemy is the last of our ancient astronomers. Ptolemy is the one who came up with an explanation to modify Aristotle's model so that it could explain retrograde motion. I think he had 2 questions on the homework too about the retrograde motion and epicycles. So Ptolemy introduced, and there's more, I haven't talked about all of Ptolemy's model. It's a little convoluted. But you have the deferent is the big circle that the planets are going around on. And then the epicycle is the little circle that they're doing on top of the big circle. And the combination of the two means that the motion for the little circle and the motion for the big circle, when you add them up, sometimes you have backward motion. And so that was a modification that Ptolemy came up with for Aristotle's model that explained the retrograde motion. When you observe the sky, you see normally, okay, let's figure out what east to west is. Normally every night, the planets move just a little bit in one direction. And then all of a sudden they'll reverse and go the other direction, then come back. You have to have an explanation. You can't just have a model that says that can't happen and say, well, good, I believe you. I observed this, but I believe this. And so it was kind of necessary to modify Aristotle's model based on observation. And then for over 1,000 years, somewhere around 1,500 years, that was the dominant model in astronomy for what's going on above the Earth. What happens to break it? To break Ptolemy, to break the faith people had in Ptolemy's model with the epicycles on the celestial sphere or on the planetary spheres.
Copernicus and Galileo.
Okay, we had Copernicus, Galileo. Most important, well, Galileo is kind of important to the story. Most important, though, Kepler. Copernicus, okay, so Copernicus reintroduced heliocentrism. It wasn't his big idea. We saw that Aristarchus had said things were heliocentric long ago. But Copernicus, once again, Said, no, it makes sense. He had circular orbits around the sun. The problem is it didn't predict positions any better than Ptolemy's model. And after 1,500 years of believing Ptolemy's model, people were not going to say, yeah, forget that. Let's go with the new one that doesn't do any better. So it really comes down, now you said Galileo, and I don't have Galileo on my slides, and I should have because he is really important. Galileo observed a number of things that just didn't make sense with the model that was believed. That is, it was believed that everything went around the Earth. And yet Galileo observed that there were moons going around Jupiter, a violation of everything around the Earth. Galileo, church, it actually goes back to Aristotle. Aristotle said this, of course he wasn't a Christian, but the Christian church took to heart that everything out there in the heavens was perfect. Here on earth, things were imperfect. And so on earth, we had lots of flaws, but out there, there would be no flaws. And the moon, sure, the moon has some flaws because it's so close to the earth. But Galileo noted sunspots, storms of the sun, which indicated flaws in the sun. And that shouldn't have been. Other things he observed, of course, the rings around Saturn. Galileo observed a lot of things. He strongly believed in the heliocentric model, but he was forced to recant because he mocked the Pope. Then we get to Johannes Kepler. Notice I skipped right over Tycho Brahe in our review. Tycho was an important character, a very interesting character, but it was his data that was analyzed by Kepler that really is pivotal. Because Kepler saw patterns. That really is the sign of intelligence by standard definitions. He saw patterns where no one else saw them. And so he deduced that you could perfectly explain the positions of the planets if instead of forcing them into circles, you allowed them to do elliptical, or oval, if you will, orbits around the sun. And so once he had that down, then things started dropping into place and he came up with 3 laws. The first one, the planets do elliptical orbits with the sun at one of the focal points. And the ellipse has 2 focal points, 2 foci. And the sun is at 1, the other one's an empty focal point. The second law, the planets sweep out a constant area per unit time. I told you that there was something important I want you to get out of it. I don't even care that you remember the part about sweeping out a constant area per unit time. What was the outcome of that is important?
Closer you are to the sun, faster it goes.
Okay. To sweep out a constant area, a planet, when it gets closer to the sun, is going to have to go faster. So you have something like, let's go to something that's not a planet. A comet. Comets are things like Pluto, but smaller, from way out there where Pluto is, that have had their orbits deviated so they're very elliptical and they fall in toward the sun. And they might be near the sun for 3 months. And they're out there far away from the sun for 50 years. Why? Because Kepler's second law says you're going to sweep out constant areas per time. So when they're far away, they hardly move to sweep out a big area. When they're close, they have to move a lot to sweep out that same area. Okay, the third one, the period squared, period being the time to do one orbit. What's the period for the Earth's orbit? It's a very simple answer. 1 year. The time it takes for the Earth to do one orbit is 1 year. So the period squared is equal to, I said proportional to because I want to make sure I have unit considerations right. But if you do it in years, then it becomes an equality. To the semi-major axis cubed. So the semi-major axis, that's equivalent to saying the average radius if it was a circle. It's the average separation. So with the Earth, its average separation from the sun is 1 astronomical unit. So you can see how that works out. 1 year squared is equal to 1 astronomical unit cubed. We can go to any other planet. So we can talk about Jupiter or Saturn, and if we measure its period in Earth years and its distance from the sun in astronomical units, that equation works out as an equality. That the period squared is equal to semi-major axis cubed. So Kepler came up with these. What was his physics for those? Nada. That was purely based on I saw the numbers and these patterns popped out at me. So from a scientific standpoint, that's fairly unfulfilling. Because remember, a hypothesis needs to be based on scientific ideas. This wasn't based on scientific ideas. It was just, look, here's what I see. So we enter Sir Isaac Newton. So chapter 3 is all about Isaac Newton. Well, not all about. There's Kepler in chapter 3. I put Kepler with the ancient astronomers, but he's a big turning point there. So Isaac Newton, in no school, Black Plague, physics time. And he came up with 3 laws of motion, developed some calculus so he could work with those, came up with the law of universal gravitation, and when he put it all together, he then had physics ideas to explain why Kepler's laws were true. Now suddenly they're scientific. Now they're based on science, not just based on, well, I saw a pattern. So Kepler comes up with these 3 laws that are observationally very clear, and people are, yeah, but why? So they believe it because it's correct. Newton comes up with reasons it's correct, and then all the scientists can breathe a sigh of relief. They know why they have it. So Newton, super important, that law of universal gravitation, force of gravity is equal to capital G, mass 1, mass 2, over the separation squared. So R is the separation. Yes, we use R for radius, and that's actually what we use it for here. That's why it's R. But it means the separation between the 2 objects. So try not to get confused with the nomenclature. Sometimes you'll see D instead of R to be the distance between the 2 objects. M is the mass, the measurement of how much material is present. This force is always attractive. So remember, you're being attracted to every other object. That's why Leslie had to push her bottle away. She's attracting it, right? Why can't she just go and pull the ball to her with gravity? It's too weak. It's there, but it's too weak. Why then is gravity holding me to the earth and not allowing me to fly free? The mass of the earth is really enormous. And so that mass of the earth times my modest mass is a really big number. And that's why we feel the Earth's gravity acting on us. And this is so vital in astronomy because it explains why the Earth is a clump. Right? Why does it just fly apart? After all, we're spinning really fast. The flat earthers would have you believe that means we should be falling apart. Gravity is holding us in. Chapter 3 and 4, I am going through pretty quickly here. In fact, this is the last slide. Does that mean chapter 4 is unimportant? No, it just means I didn't want to put a whole bunch of slides after this. So in chapter 4, we have ideas like the seasons. What causes the seasons on Earth?
Because of the 20 degree
23 and a half. Yeah.
The tilt of the Earth.
The tilt of the Earth.
Around the sun.
And its orbit around the sun. That's perfect. People coming into a class like this very often think that the Earth is just closer to the sun in the summertime. I mean, if it was, that would make sense. But when is the Earth closest to the sun? In January. And that wouldn't explain it then, would it? Now, if you were in the southern hemisphere, sure, that would explain. January is the middle of the summer. But we're in the northern hemisphere, and we know, that's not it. But that tilt, if the sun is here, the northern hemisphere is going to be getting more direct sunlight. So that means that the amount of energy you're receiving per second is bigger. And you have sunlight for a longer period of time. Hence, you get more energy per second for a bigger number of seconds. A lot more energy coming in, raising the temperatures. Just watched Groundhog Day for some reason, so I'm into my weather. Winter. When it's winter, if the Earth's tilted like this and the sun's over here in the northern hemisphere, the sunlight is very glancing, so you're getting less energy per second, and You spend more time at nighttime than you do in daytime. In fact, we have the Arctic Circle. In the Arctic Circle, in the wintertime, the sun never makes it above the horizon. The Earth is spinning like this. The top of the Earth is up here. Anything that's closer to the pole than there is never going to see sunlight. And so the Arctic Circle is defined as the region that's 23.5 degrees from the north celestial pole. The Antarctic Circle, 23.5 degrees from the south celestial pole. Likewise, the tropics are defined as the regions that at some point in the year the sun's going to be overhead. So that's 23.5 degrees north for the Tropic of Cancer, 23.5 degrees south for the Tropic of Capricorn. So the tropics is the region between those two lines. So, when I was a kid growing up in the tropics, I just knew it was in the tropics. It was a place that was hot. We had rainy season and dry season. Now that I'm an astronomy teacher, I know why it's the tropics. It's not because we have rainy season and dry season. Lunar phases. Okay, I've already touched on the lunar phases, so don't need to go through that again. Ocean tides. What causes ocean tides? Okay, the moon is the primary. It's not the only, it's the primary. What about the moon? Okay, the gravitational pull. But it's not the strength of the gravitational pull. The gravitational pull of the sun on the Earth is far greater than the gravitational pull of the moon on the Earth. So it's not just the strength of it. What is it about the gravitational pull? The what?
I don't know how to say it. I'm wrong.
There's nothing wrong with being incorrect.
Is it because it's closer?
Because it's closer, the difference in the gravitational force is bigger. The gravitational force varies more rapidly when you get farther away if you're close than if you're far. And so the difference in the gravitational force from the moon on one side of the Earth to the gravitational force of the moon on the other side of the Earth is much bigger than the difference in gravitational force of the sun on one side of the Earth and the sun on the other side of the Earth. So we call that tidal forces, the difference in the gravitational force from one side of the Earth to the other. The moon's tidal force is much bigger than the sun's because the moon is much closer, which I believe is what Leslie said. And so the moon is the prime cause of our tides. So make sure you understand, where do you have a high tide if the Earth wasn't spinning? Where would it be? On the high tide would be on the side facing the moon and on the other side. So two high tides at the same time. Because the Earth is spinning, how has that changed?
The tide's a little bit ahead.
Yeah, the tides are shifted just a little bit ahead. And that has the bizarre outcome of transferring energy to the moon, speeding the moon up. You speed the moon up, and it starts getting farther away. So the moon is very slowly moving away from the Earth because of this tidal interaction. What about the sun in all of this? Well, it has an effect. Remember the words spring tide and neap tide? Spring tide is the biggest difference between high tide and low tide. And that occurs when you have a straight line between the sun, the moon, and the Earth. That would be either the moon is in opposition or in this case, it's just a conjunction. Because it doesn't go around the sun, there's no superior or inferior conjunction here. So you have, those are what cause the spring tide, because the tidal effect of the sun and the moon are both acting in the same direction. The neap tide is the smallest difference between high tide and low tide, and that's going to occur when you form a right angle or a quadrature between the sun and the moon as these revert. Eclipses, finally, we've already talked about those, so I'm done with my review. Have I covered everything on the test? No, I have not. But I've tried to cover the highlights. I've tried to cover, 75% of what will be on the test. The things that are, the most outstanding things. And of course, I already covered more than 10% of the test just by talking about the one question about the scientific method. Make sure you don't miss that. Don't let me down. You know it's coming. I talked about the listing. That was 4 of the 8 points. What are the other 4 points? It has to be applied. So I'm going to give you an observation. Remember, what was the first step? Observe something interesting. So I'm going to give you an observation. I'm not going to say this is the first step. You'll say for the first step, I observed this. You don't have to quote it exactly, but it should be the same idea as what the observation I give you is, because that's the first step. So then you have to remember how to apply the next three. So the next three is you're going to have to give a plausible explanation based on scientific ideas of why the thing that's observed occurs. And then a test that can test a prediction of that. And remember, the test should not going to go back and make the measurement that was my observation. That would just be circular. It needs to be a new prediction, something you don't know what's going to happen. All right, let's go. Who's with me?